the next speaker is Mario Krenn. He studied also quantum physics and did his PhD at the TU Technical University in Vienna. Then he moved on to do a fellowship with the Erwin Schrödinger Fellowship at the University of Toronto. And later this year, he will join as a group leader at the Max Planck Institute for the Science of Light in Erlangen. Good, and he is talking about a journey from computer-designed quantum experiments to computer-inspired scientific understanding. Good, Mario.
Thank you. Can you see my screen? It's not full screen.
It's not full screen yet, but now it works. Yes, now it works.
Okay. Yeah. Thank you a lot for the introduction. Yeah, my name is Mario Krenn, and I will join the Max Planck Institute for the Science of Light in September. And very short advertisement: if you are interested working with us, especially as a postdoc, please look at my website. We have some open positions. Okay. Now let's go to the scientific part of my talk. 1 second. Okay. So there are many fields in physics that exploit actually computers to design questions with many diverse computational methods and AI methods. And I will give a few examples for this. One very famous example is actually in plasma physics, where the coils of the Wendelstein 7X nuclear fusion reactor have only made possible by design at supercomputers. Another example is in nanophotonics, where very impressive properties of photonic devices have been designed using computers and AI methods. For instance, this is an on-chip particle accelerator that was published 1 year ago. Another field is chemistry, where computer designs and AI methods are commonly used both in industry and in academia, with thousands of papers in the last few years. So, for instance, this is an inhibitor for a gene called DDR that is researched in connection to cancer treatment. And it is designed by a deep learning method. It has been actually produced in labs and is now at the stage of animal trials. So here we'll focus on computer design methods for quantum experiments. And to set this research and the goal into a context and to see where we can go into the future, we can classify the current maturity, roughly, of computer algorithms into several classes. So here, for instance, class 0 algorithm are those that can actually solve physical questions, such as design of quantum experiments or finding equations of motions for a physical system that we have seen yesterday, and so on. So in this class, there are a lot of exciting application of machine learning and AI technologies that could have a large impact in the future, but that are not at the stage yet that they can apply to solve actually new and open problems. Examples here are algorithms that can identify the autonomous shift from the geocentric to the heliocentric worldview that we just heard in the talk before, that we also heard actually yesterday, or the discovery of phases in matter using unsupervised learning methods. So those algorithms are really exciting, and hopefully they can apply it in the future to open problems. Now, algorithms that actually can solve open problems, we could classify in class 1. Those results are, of course, exciting, but in order to be actually practical and really impactful, we actually want more. First, we might want that the solutions are in some way experimentally accessible and can be demonstrated or even used in laboratories or the real world. For example, in material science, there are molecules that are known that can improve energy conversions in photovoltaic, which would be great. However, no one knows how to produce those, and especially not at not efficiently at the scale that would be required. So in some way, it's very important that those solutions are also accessible experimentally. On the other hand, as scientists, we even want more. We want to understand the solutions from our computer algorithms. So when a computer comes up with a solution, we don't want to accept it as a black box. We want to understand the concepts and the underlying ideas of the solutions. So this is what we call class 2B algorithms, where humans can actually learn new physics or new concepts from algorithms. And finally, class 3 algorithms, we call those that are both experimentally, that can produce both experimentally and conceptually progress in their solutions. And in the rest of the talk now, I will explain how in quantum optics, we've made steps towards higher algorithms or higher classes of those algorithms to reach both experimental feasibility as well as new concepts. And this all started a few years ago, where we wanted to create and observe new complex entanglement in the laboratory. So in particular, we wanted to create multi-particle entangled states that go beyond qubits. So let me explain what this means. The most commonly known form of entanglement consists of two particles that are entangled in two properties. For instance, you can think about two photons, where both photons are either red or green. So this is a so-called Bell state and is experimentally investigated for many decades. The exciting thing about this state is that the photons, before you measure them, they don't have a well-defined state. So they are not definite red or definite green. But only when you measure them, they take one of the colors. And at the same moment, its partner photon has the same color. So in order to increase the complexity of these states, we could now increase the number of particles in this state. For example, we could have now 3 particles, where all 3 particles are either red or green. This is a so-called Greenberger-Horn-Zeilinger state and explored for roughly 20 years experimentally. And it is actually a very important state for quantum computing, basically in some way a resource state, or at least if you can create states like this, you can also create other very important resource states for quantum computing. Alternatively, one can add more colors in the system. In this case, we have 2 photons, where both photons are either red or green or blue. And again, before you measure them, they don't have a well-defined color. This is so-called high-dimensional entanglement, and very much investigate in the last also roughly 20 years, because here each photon carries more than 1 bit of information. So this is very interesting for quantum communication tasks, where you have a much higher information density that you can send. So we wanted to analyze now quantum entanglement that have more than 2 particles and more than 2 colors. So a state could look like this, where you have 3 particles, where all 3 particles are either red or green or blue. So the first question, if you want to create this, is how does actually the experimental setup look like that can create such a quantum state that we had in mind? So that was a question that we actually solved on a regular basis. Usually it's like that. You think about the state that you want to create, and then you sit down or you go to the blackboard, you write down a bit based on your intuition, and usually you find the solution rather quickly. But for that case, it was different. Actually, it took for several weeks, my colleagues and I were trying to find the experimental configuration that could produce such a state. But all of our attempts that we had, and there were a lot of different ideas, all of them failed. So in some way, the question was, why can we not create this? And I was very puzzled by this. And after some time, I thought maybe we need to go to a different way to actually design such systems that are not based on human intuition. And at that point, I started to write computer algorithms that actually help in the design process. And the idea of the computer algorithm that I came up with was the following. We start with a toolbox that have all optical elements that we have in our lab. And in the beginning, we start to arrange those elements in a random way. Then we calculate a number of properties of the setup and of the state that are easy to compute and that we can use as cheap criteria, such that we can reject a number of states immediately before we compute the more expensive criteria. Then if the setup that we created satisfies all of those simple criteria, we compute the full criteria. And we compute whether the state actually has the property that we are interested in. If yes, then the algorithm simplifies the solution and reports it to the user. Furthermore, the solution gets added into the toolbox such that in the next iteration of the algorithm, the algorithm can already access these more complex and useful tools. And this speeds up the discovery process for more complex systems by several orders of magnitude. So this algorithm is actually rather simple, but to the best of our knowledge, no one has used computer-designed quantum experiments at that time. And furthermore, this approach was in some way spot on for our problem, because a few hours after I started the algorithm, it actually discovered the experimental setup that can produce the quantum state that we had in mind, and that we as humans were not able to find for a number of weeks. So this has allowed us in an actual multi-year project to produce this new type of quantum entanglement in the lab and observe some of its properties. So over the next few years, we used variations of these algorithms to design other quantum systems and techniques that we were not able to find by ourselves. For example, we found an entirely new way to measure photons with complex spatial structures. And this has important consequences for quantum communication, but especially also for classical communication. So that's a technique that can also be used in classical communication techniques. And very recently, actually, we've applied this algorithm, a variation of this algorithm, to a non-photonic system. We found a quantum circuit for quantum computers that produce a never observed complex type of entanglement in a superconducting quantum device. So this was made possible by a special hardware access that we got by IBM's quantum computing team. And then the first iteration of the quantum circuit that can produce the state that we were interested in also came from my computer algorithm, because we ourselves, again, were not able to find a practically suitable solution. So this algorithm has allowed for the observation of new quantum properties in the laboratory. But for me, even more surprising is the fact that we can use this algorithm to get new ideas and inspiration for new concepts in quantum physics. For one example that I would like to mention briefly was by looking at outliers of a large computation. We found a concept for an entirely new way to generate quantum entanglement in photons. This technique could have been discovered 25 years by human researchers, but they have been this technique has been overlooked and has now only been discovered now with the help of my computer algorithm. So we call this computer-inspired idea entanglement by path identity. I will not go into the details how this works, but just explain a very basic idea behind it. So the very basic idea is that the computer found a way how to arrange photon pair sources in such a way that it can independently manipulate the individual terms of the quantum state. And this is done by overlapping the paths of photons and thereby exploiting a quantum interference effect that I have actually not allowed explicitly in the toolbox. But the computer found a way to implicitly use exactly that technique and thereby kind of circumvented this restriction that I imposed unconsciously and found this technique. And this technique can be used to generate a large number of different quantum systems in a very controlled way, in a very different way than it has been done before. And specifically, it also shows an idea for a scalable source of high-dimensional two-particle entanglement, which is useful for quantum communication. Again, because this high-dimensional entanglement is has much more information encoded in the individual photons. So, and a proof of principle experiment of this scalable source has very recently been done by some of my colleagues in Vienna. Furthermore, we found that this type of entanglement generation is directly related to colored graphs. So therefore, we in some way found a hidden bridge between quantum optics and graph theory. So this allows us to translate questions in quantum physics to graph theory, answer it here, and translate the question back to quantum physics. So in that way, this connection has led to a number of insight into new quantum interference and new quantum computing techniques. And I would like to mention one, why this is possible. So in graph theory, there are a number of properties which are known to be extremely difficult to calculate. With this bridge, what we have found is that we can create quantum states that encode in their amplitude exactly the solutions of those very difficult questions. That means there's no way basically to compute the final quantum state feasibly in a classical machine. And that goes into the direction of quantum advantage and quantum supremacy experiments. So furthermore, we have found with this technique also a new type of non-local multi-particle quantum interference. And this has just a few months ago been demonstrated by some of my collaborators at USDC in China using an integrated photonic chip where they were able to encode a number of photon pair sources in a very coherent way. So at this point, we see that we can not only get solutions to questions in quantum optics, but we can also learn from those solutions. But understanding solutions from the computer actually take many days or even weeks. So a question is, can we find computer algorithms that help us to find or understand solutions much easier? And to address this question, we need to know what does it actually mean to understand, or what does it mean to scientifically understand? And there we can actually get some inspiration from the philosophy of science. And just a few years ago, actually, the philosopher Henk de Rek has published a prize-winning book exactly on that question. So he has overviewed the development of scientific understanding and has given a new pragmatic way to think about it. So he says that scientists can understand the phenomenon if they can recognize qualitatively characteristic consequences without performing exact computations. So that means in some way, scientific understanding is connected to the skill to use concepts fruitfully without exact calculations. So with this inspiration from philosophy in mind, we go further and develop now a new quantum algorithm. One which actually helps us to get understanding or to understand those solutions much faster. So the basis of the algorithm is actually the graph experiment relation that I explained to you before, that I showed to you before, that we also found through computers. So here we exploit the fact that every quantum experiment that we can build in our lab can be described by a colored weighted graph. And at the same time, every colored weighted graph encodes the blueprint of a quantum optical experiment. Here, every vertex stands for a photon path, every edge stands for a photon pair, a correlated photon pair. The edge weight stands for the amplitude or the probability of that photon pair, and the color in some way stands for the property of the state or of this photon pair. And thereby, the most general thing that we can do in a quantum optical laboratory is can be described by a complete colored weighted graph. This weighted color graph now describes at the same time the quantum state and a quantum experiment. That means that we can write now the quantum state and each of its properties in terms of the weights of the graphs. For this, we introduce something that's called weight function, which is a function that we can very easily derive from the graph. And if we apply this weight function to the vacuum, we actually get the resulting quantum state. So this connection allows us now to use highly efficient gradient-based methods to find new solutions. So in a design process, now we start with a complete graph and we design a loss function. And let's say, for example, we are interested in a setup that creates a certain state. Now, in that case, the loss function could be 1 minus the fidelity of the state, or that's something like 1 minus the quality of the state generation. In the loss function, we also add the L1 regularization term that motivates the algorithm to find solutions where a lot of the weights vanish. That means a lot of the edges get removed. And in order to solve this loss function, we can use an iterative method called Pfgs Algorithm, which uses at the same time gradients and higher order derivatives of the loss function. But we can not only optimize the weights of the graph, but we can actually optimize the topology of the graph. And we do so by running the optimization, find the weight configuration, and remove the smallest weights, and then restart the parametric optimization. Then again, remove the smallest weights, and in this case, in some way extract the conceptual core of the solution from this complete graph. And a human can then usually look at the solution and immediately understand the solution and the reasons behind why it works. So let me briefly show how this algorithm performs in a number of benchmarks. So in the first benchmark, we task the algorithm to find a number of free-particle high-dimensional states. We restrict the state space in such a way that we know that there are exactly 81 solutions possible. So the algorithm that I explained to you in the very beginning was able to find roughly 51 of the 81 solutions in roughly 150 hours. An extension that was a collaboration with the group of Hans Prigel was a reinforcement learning algorithm. It found roughly 17 of the solution in 10 hours. And with our new algorithm, we find the 17 states, or the first 17 states, in roughly 2 seconds, and 51 states in roughly 15 minutes. So we see the algorithm is clearly orders of magnitude faster than previous approaches.
Mario, you have about 5 minutes, okay?
Yeah, that is fine. And yeah, so it is clearly much faster than previous approaches. And I skip this. And because it is so much faster than previous approaches, we can actually apply it to new open questions. And let me show you one open question. It's the last example I want to show. So in quantum optics, one important question is how to create heralded entanglement. So the problem in quantum optics is that the sources of entanglement are probabilistic pair sources. That means they create photon pairs at a random time, and you never know when they create a photon pair. Only when you measure them, you knew that they were there. But this is unfortunate for a number of applications. For instance, in quantum computing, you would need to know exactly when the photons have been created. And a setup that can actually tell you when the photons are created or when the photon pair is created, that is called a heralded entanglement. And indeed, for heralded two-particle, two-dimensional entanglement, there are solutions that have been investigated for a few years, but much less is known for this more complex systems. So therefore, our first question that we asked, which was not known before, is how does a setup look like that can create heralded three-dimensional entanglement? So in this case, we start again with a complete graph, and the vertex A and B are the vertices where the entangled photon pair should emerge. And the detectors C, D, E, F, G, and H are trigger detectors. And if the trigger detectors click at the same time, we want to be sure that the output is a three-dimensional entangled state. So this is our objective. The main problem here is that in this case, we need 8 photons, but already 8 photons because 2 output and 6 heralding detectors. But already 6 photons can make the heralding detectors click, and this would have no output. And this is exactly what we want to prevent. We want to prevent that the 6 detectors say now there's an output, but there is no output. It means they somehow herald the vacuum. And so we start to search for this solution. And actually within minutes, the algorithm found a solution. And the solution was then structurally optimized, and we were basically immediately able to understand the underlying idea. And I found this underlying idea quite remarkable. What the algorithm has done is it was able to create 2 of these cases where you have no output of the setup. So these are actually the cases that we want to prevent, and the algorithm produced now 2 of those in the same setup. But it did it in a way that one of those had a negative sign, so they had the opposite sign. And then the quantum state, they then actually canceled each other. So what the algorithm has somehow developed was the idea of destructive vacuum interference. So here you have destructive interference of this heralded vacuum contribution. And I've never seen this idea mentioned before anywhere in the literature. And as soon as we were able to understand this idea, we were immediately able to generalize it to many other cases, to higher dimensional and also to multi-particle cases by hand without using the computer anymore, just by using this new idea, this new concept that the computer has shown to us. So we have learned a new idea, a new concept from the solution of the algorithm, and we're able to apply it in a fruitful way to other systems without computing. And this is according to the criteria of Henk de Rek, the philosopher that I mentioned in the beginning, precisely what it means to get to have scientific understanding. And we got it in this case from a computer. Okay, let me now come to the end of my talk and to a conclusion. At the big picture, we now have in quantum optics an algorithm that is powerful enough to be able to solve open and potentially long-standing questions. And we can not only solve these questions, but we can actually understand the solutions basically immediately because of this very interpretable, understandable representation. And from that, we can learn and understand new concepts, new ideas, and new intuitions from the algorithm. So there are now many applications that we could think about. For instance, I'm very excited about quantum enhanced microscopes, measurements, and so on. But another point that I'm very excited about is that very recently we have found that this representation that seemed to be only useful for quantum optics can actually be generalized to other systems that have nothing to do with photons, to other quantum systems, for instance, to the design of quantum circuits for quantum computers. This is a question that is independent of photons, but we found a way to use our representation and basically exactly the same ideas to also solve questions in quantum circuit design. So in some way, I'm hoping that this representation can be generalized to many other quantum systems, potentially other classical systems, classical physical systems as well, that we have a very efficient design algorithm in this other quantum domain, so physical domain, where we can understand the solution and where we can learn new concepts from the solution. And let me finish with a last thought. So what I've learned, what I've found most interesting is in this project is somehow that philosophy of science seems to be a very productive guiding principle for the development of new AI algorithms in science. For example, questions like what is creativity, what is surprising, what is intuition, or in this case, what does understanding mean? Philosophers, I'm sure, have very interesting things to say about this. And if we take this serious, if we read this, if we try to see how to apply it, I think we can actually go to some next level of AI algorithms, those that can contribute much more creatively at the conceptual level to science. I would find this very exciting. Okay, thank you.